We have mentioned that one way to compute cohomology is by using long exact sequence of cohomology induced by short exact sequence of cochain complexes. One special case of that is the Mayer-Vietoris sequence. In this video, we're gonna introduce the short exact sequence of cochain complex associated to this. Then in the next video, we're gonna talk about the long exact sequence, the Mayer-Vietoris sequence. After that, we are gonna use the Mayer-Vietoris sequence to give another computation of the cohomology group of the circle, as well as compute the cohomology group of a torus and a general compact surface of genus G. So let us first introduce the short exact sequence of cochain complexes that induce the Mayer-Vietoris sequence. Mayer-Vietoris sequence is used to compute cohomology of a manifold in terms of a covering. So the setup is suppose that M is covered by open sets U and V. Then we claim that for every K, we will have the following short exact sequence, which then induce a short exact sequence of cochain complexes. So let's explain the maps in this short exact sequence. Okay, so the first map I, we call this the restriction map. Given any K form sigma here on M, we just send it to its restriction to U and its restriction to V. Let's recall the definition of this restriction. So we have an inclusion map from this open set U into M, right? And so we can define the restriction of sigma to U to just be the pullback of sigma under this restriction map. Alright, so that's the definition of this restriction map, and we immediately see injectivity here. Because if sigma restricts to 0 on U and 0 on V, then sigma itself must be the 0 form. Good, so now let's talk about the second map. We call this the difference map, and true to its name, it sends a pair of K form to its different. So let us explain what we mean. So let's say we have K form omega on U and then a K form tau on V. Note that we have inclusion map from U intersect with V into this U and V. And as before, the pullback of omega under this inclusion map is going to be a form on U intersect with V, right? Which we define to be this omega restricted to U intersect with V. And this pullback of tau, similarly, it's also a form here. And we just define the image of omega comma tau under this map to be this different. So this is a K form on U intersect with V. With this definition of J, we immediately see exactness here, right? What do we mean? Remember, exactness, that means that the kernel of J is equal to the image of I. Okay, so let's see that. So first, it's easy to see that image of I must lie in this kernel, because the image of I are just gonna be the pairs that are restriction of a given global form sigma, right? So their difference is just gonna be 0. Because this agree on the intersection, because they both comes from sigma. Conversely, let's see why this kernel lie inside the image. So what does it mean for omega comma tau to lie in this kernel of J? That just means that they agree on intersection, right? This difference has to be 0. Well, if they agree on intersection, then they must glue together to a global form, sigma. In other words, they're just gonna be the restriction of a form sigma. So they lie in the image of I. Thus we have exactness here. So to show that this sequence is exact, it remains just to show that this map J, this difference map, is surjective. So let's prove this surjectivity for the case when K is equal to 0. Because in that case, all of these omega naught are just functions, smooth functions, and we can use our intuition about functions. The case for the general K is exactly the same. Alright, so let's take an f here, which is a smooth function over on U intersect with V, right? So let's say this is f. Now we want to construct fv and minus fu so that f is just gonna be the sum of fu and fv on U intersect with V. Our idea is to use a partition of unity. If rho u and rho v are a partition of unity subordinate to U and V, then we immediately have that on U intersect with V, f is just gonna be equal to this. because you know that rho u plus rho v is equal to 1. Okay, so can we just take this to be fu and then fv? No, there is some problem here. Note that this expression is only defined on u intersect with v because f is only defined on u intersect with v, so this is not a function on the whole of u or on the whole of v. Thus, we need to extend these functions. Well, at first, because there is a u here, you might think of extending this to the whole of u, but it's really unclear how to do that, right? So this is the rho uf. It's really unclear how we would extend it smoothly over here. However, it's really clear how to extend it smoothly on v, because it's just 0 here, so we could just extend it by 0 on v. So we can define the function fv to be extension by 0 of this rho uf to v. And similarly, we can extend this rho vf to u by 0. These are clearly smooth, and f is clearly the sum of fe with fu. So f is the image of this under j, and thus j is surjective at the level 0. Now in a general level k, we can repeat exactly the same proof, just replacing f with any k-form omega. Thus, this is a short exact sequence, and thus it induces a short exact sequence of cochain complex.